Hello. Today I'll be talking about cross-site scripting, types of cross-site scripting, how it's detected, and how we protect against it. Cross-site scripting, abbreviated XSS, since the CSS acronym was already taken by cascading style sheets, is currently the number 7 vulnerability in the OWASP Top 10 Web Application Risks from 2017. We're expecting a new list this year or next, but XSS will likely still feature prominently on it. XSS is a type of injection attack. Malicious input is injected into a website and executed as code rather than being treated as just user data. They are so common because they can occur anywhere that a user is able to input data, intentionally or otherwise. Cross-site scripting is commonly implemented by inserting code payloads into script tags, JavaScript events, event attributes, image attributes, iframe tags, and more. And although it's possible to filter against inclusion of these tags in user input, there are still many ways to circumvent that filtering. In this case, the greater than and less than symbols are URL encoded. Because the code is running in the context of a trusted web page or application, it can access all of the same resources as good code. Cookies, session tokens, and other sensitive information are all accessible. An attacker exploiting XSS can then impersonate their victim, deface the website affected, access the user's clipboard, and gather user credentials through keylogging. If the website interacts with sensitive information, a banking or healthcare site, for example, then that data is also at risk. And the attacker can employ all of this information to carry out more complex and serious attacks, such as cross-site request forgeries. We typically distinguish between 3 types of XSS: reflected, stored, and DOM-based. Although it has been suggested that it's more sensible for researchers to distinguish between server-side and client-side XSS instead, it's simpler to conceptualize the 3 common types, and I'll stick with that categorization here. The most common types of cross-site scripting is reflected XSS. In which malicious code is immediately executed in the current browser session. The code does not remain persistent in the application, but it can be packaged into a malicious URL to be used in phishing emails and watering hole attacks. For this reason, they are also known as non-persistent XSS attacks or first-order XSS attacks. While vulnerability scanners will detect most reflected XSS avenues, it's important to test all of the input vectors manually for more complex filter bypasses. All detection attempts must begin by determining all of the input vectors, every place that can accept user input, including HTTP parameters, hidden form fields, predefined selection values, and more. All of these can be manipulated, and they can be manipulated outside of the application itself by intercepting requests using a web proxy like Burp Suite. Where time and resources permit, in-depth fuzzing, that is, providing random unexpected data, should also be conducted on each vector. While less common than reflected cross-site scripting, stored XSS is far more dangerous. In stored XSS, the malicious code persists on the website and has the potential to affect any and all users that visit the site. Instead of being directly executed in the attacker's current session, the code is stored in a message form, comment field, or other persistent feature to be run every time these features are loaded by a user's browser. For this reason, stored XSS attacks are also referred to as persistent XSS attacks, or second-order XSS attacks. And if the user who visits the site is also an administrator with elevated privileges, the attack may also be executed with those elevated privileges. Again, automated tools exist for identifying most vulnerable input vectors for user input to be stored and displayed by the application. Identification of input vectors, standard and out of band, is still key here. Manual and automated testing should focus on forums and comment sections, user profiles, shopping carts, and blogs. But a thorough examination of administration areas of an application for any displayed user input is essential to prevent execution of malicious code with those administrative privileges. The Document Object Model, or DOM, is a programming API for HTML and XML, representing each part of the document as an object. These source objects may also have methods used in object-oriented programming languages like JavaScript to access and interpret the document dynamically. Sensitive methods, called sinks, have the potential then to be maliciously employed. These sinks can then write to the document object without leaving any evidence in the page's HTML source code or being transmitted to the web server running the site. DOM XSS is particularly nasty because it's not mitigated by server-side filtering. None of the code leaves the browser. In this example, the victim's browser would parse the HTML page into the DOM, which contains the document object that has a URL property. When the parser reaches the script in the provided URL, it executes the script and modifies the website document itself, instead of relying on the document to explicitly display unfiltered data, or on that data being stored on the web server. Now, because JavaScript dynamically generates web pages, it is not sufficient to simply examine typical input vectors. All of the executable JavaScript in the page source code and its externally linked sources must also be carefully examined. Most of the JavaScript code in use on websites today resides in commonly used libraries that were not developed by the application's programmers. This means that automated testing is typically inadequate, and research suggests that half or more of websites are still vulnerable to DOM XSS. Ultimately, we don't just want to detect XSS vulnerabilities, but to mitigate against their exploitation altogether. Now, as testing is conducted, it's necessary to determine the impact of the vulnerability. The ability to turn your or a single victim's page green is not a substantial business risk and may not require elaborate remediation. However, if there is a significant business risk, then it becomes essential to ensure that user input is further sanitized, both at the client and at the server. Now, this may require identifying sensitive characters that were not properly encoded, replaced, or filtered against. Increasingly, this is being handled by input sanitization libraries specifically designed to prevent injection attacks of all kinds. HTTP responses can also be secured against transmission of HTML or JavaScript where none should be present using the content type and X-content type option headers. Any code that accesses the document object model and has the potential to modify it should be carefully reviewed and revised to reduce access to sensitive methods. On the server side, it's recommended to establish strictly limited IPS policies, allowing only the expected parameters, sources, and headers to be transmitted. And finally, content security policy headers and content security policy meta-elements can be used to restrict which domains the browser should accept executable code from. OWASP, the Open Web Application Security Project, is a leader in resources for understanding, testing, and mitigating cross-site scripting vulnerabilities, and provide many excellent and free training, testing, and remediation resources. Portswigger, the developers of the Burp Suite web proxy, also offer excellent free training and detection resources, and I've drawn extensively from those projects here. While XSS vulnerabilities have received substantial attention from SecDevOps, security researchers, and bug bounty hunters in recent years, it remains a persistent and serious security flaw. Thank you.